1. Okay, next up is precipitation. Now, the word precipitation, of course, brings to mind rain or snow or whatever. In chemistry, precipitation refers more to the solid aspect there rather than the liquid aspect of a result of a chemical reaction. Whenever you add two substances together, particularly in a double displacement reaction, is a very good example of this. This is one such example. We take calcium chloride dissolved in water, aqueous solution, and an aqueous magnesium sulfate. In the past, we've always said that in order for a double displacement reaction to work, you have to have at least one solid. In this case, we have exactly one solid. Calcium sulfate is a solid. And then magnesium chloride stays in aqueous form, so we don't see it, but we do see the calcium sulfate. Now, in the past, I had given you polyatomic ion sheets that kind of gave you clues as to when to expect an insoluble compound like calcium sulfate. However, sulfates and chlorides are not on the list, so how would you know which one you have? The best way to do it is by looking at the charts on pages 773 and 774, which is the KSP charts. If you have a KSP chart that is simply telling you that those compounds are technically insoluble, and it turns out this calcium sulfate is on that list, where magnesium chloride is not on that list. So if you didn't know, which in this case you would not know, based upon what I've given you, that you would have to look at the chart and see that yes, indeed, CaSO4 is our precipitate. We call this a precipitate. It precipitates out like snow. That is our precipitate. So that's the basis of what we're going to talk about today. Now, another thing that we're talking about today that we've talked about in the past is the concept of Q and how it relates to K. And since we are dealing with equilibrium conditions, meaning that you have KSPs, like we had KAs and KBs and KCs and KPs and all that stuff, this is going to be involving KSP. Where we said K is the actual quantity at equilibrium, Q is questionable. We're not sure if it's at equilibrium or not. So Q for questionable is what we use. And if we see that the value that we get for our concentrations plugged into the K expression, we still use the same K expression we had for KSP or whatever, but we replace it with Q because we're not sure if it is that. But if it is that number, then we know that that is indeed at equilibrium and is a KSP. What we are going to use it for this time is that whether we're going to expect a precipitate or not. So basically, if Q turns out to be less than KSP, we would expect no precipitate. Even though it's not on the chart, we don't have enough of concentrations to get to that point where we get the KSP. Okay, so it's kind of a fine line, but just because it's in the chart doesn't mean it's always insoluble. It is insoluble when you reach a certain point of the right amount of concentrations of your substances to get to that point. Most of the time, in fact, I'd probably say 99% of the time, you will find that precipitate will occur for those compounds on that list. But every once in a while, it's not going to happen. And this is how you predict. You look at the value Q compared to KSP. And likewise, or should I say contrary to that, if Q is greater than or equal to KSP, then there will be a precipitate. And precipitate is abbreviated as PPT. And it's a whole lot easier to write than precipitate. Okay? So, let's take a look on page 796, problem number 39, part A, and how we would use this. Okay? So, page 796, 39A. And we are asked to find if we have a precipitate if these two concentrations are brought together. So we have the concentration of barium, 2 positive, which is 0.020 mole per liter. And we're given the concentration of fluoride ions as 0.012 0.15 moles per liter. And the question here is, will there be a precipitate? Yes or no? In order to do that, we have to identify the compound that's being created by the addition of these two together. So let's take a look at that, shall we? Ba2 positive aqueous plus F negative aqueous. Now, we have a positive 2 ion and we have a negative 1 ion. That means in order for them to get together, we have to have 2 of these fluorides. So the compound BAF will not be the compound, it will be BAF2. Because positive 2, negative 2 added to 0. This will most likely be a solid, we're about to find out, but we're going to put it down there anyway. But if we have a 2 there, then we have to put a 2 in front. Please don't put a 2 behind it. Even though it's behind there, don't put it behind here because fluoride ions are not diatomic. Fluorine atoms are diatomic. But ions and atoms are 2 completely different creatures. An ion is where it has the maximum number of electrons in its outer shell. It doesn't want any more. The fact that it didn't have enough when it was an atom wanted to have 2 to create that single bond between the 2 of them so they can pretend like they both had 8 because they're sharing 2. That's not what's happening here. This is an ion full of electron, doesn't want any more, don't put a 2 there. Put the 2 in front to balance the atoms out, not the charges there. Okay? Now, since this is technically the insoluble salt, we need to find the KSP for barium fluoride. So, barium fluoride on page 772 is 1.0 times 10 to the negative 6. And the KSP expression that would go with that is Ba2 positive times, and that's coming from that right there, and then this right here, fluoride, the fact that you have a 2 coefficient means you're going to have an exponent of 2 here. Be careful on that. Make sure you take care of that. Now, what we're going to do at this point is we're going to use the Q value for this. We're going to find the Q. Not we're going to use it. We're going to find the Q value for this by plugging in the concentrations that were given to us in the problem. 0.020 for this and 0.015 for this. And then we're going to compare it to the 1.0 times 10 to the negative 6. So this can be 0.020 moles per liter here times 0.015 moles per liter quantity squared, because that exponent 2 there. We multiply this stuff out, and we get 4.50 times 10 to the negative 6. We don't worry about a label for K or Q. But what we do now know is that the value Q here is greater than the value of the KSP. Therefore, and the little triangle of dots is an abbreviation for therefore, and when you go to college you have to write notes if your professor going blah, 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 blah. But that's one of those things you probably should want to learn. Anyway, if you don't, whatever. But that is telling you, since Q is greater than kilograms, that's so nice. Why would I put kilograms in there? That was a massive mistake, people. Don't do, never mind, that was dumb. KSP. Massive mistake, kilograms, whatever. Because of that, though, that Q is greater than KSP, a precipitate will occur. So we know precipitate does indeed happen. Okay? All right, let's take a look at another problem, problem number 43 in your textbook, page 796.